Welcome to lesson 26, the Fundamental Theorem of Calculus. Sounds pretty important, right? So what the Fundamental Theorem of Calculus is going to do is it's going to connect differential and integral calculus. So we're going to figure out what the relationship is between derivatives and integrals. That is why it's so fundamental. So if we just lay a little bit of groundwork for what we've done so far in the world of calculus, you have sort of two branches. So the differential calculus was based on those tangent lines, that the tangent problem is kind of where that aspect of calculus or branch of calculus started. And integral calculus, which is based on the area problem, right, are related. And in fact, we are about to discover that taking a derivative and taking an integral are inverse operations. So basically, they undo each other. So I'm going to just show you kind of a very crude visualization that can help you kind of think of that, of how these two things could be inverses. So I'm going to take a function f of x, and I'm going to draw it twice, or something close to it, twice. And we're going to talk a little bit about differentiation. So what did we do in differentiation? We were trying to find the equation of a tangent line, right? And so we took 2 points, or the slope of the tangent line. So we took 2 points and we made that secant line. We had a delta y and a delta x. And the idea, the slope of that secant line, which is change in y over change in x, was that we were trying to make one of these points basically become as close as possible as we could to the other. So we were taking the limit as the delta x went to 0. Okay. So that's a very crude summary of how we started looking at differentiation. Whereas integration, we were taking areas, and we had a delta x. And this is really an f of x, but we could think of it as a delta y, right? Because it's from the y coordinate down to 0. And we were trying to find an area, so we were multiplying these two things together, the height times the width. But we were also trying to make this width as small as possible. So we were also trying to do a limit as delta x approaches 0. And so you can see that we are doing the same limits, but in one place we are dividing and in one place we are multiplying. And multiplication and division are inverse operations, right? They undo each other. So the inventors of calculus linked these two operations in the same way. So the fundamental theorem of calculus has 2 parts. And we definitely end up using the second part the most, but it's the first part that actually establishes this inverse relationship between derivatives and integrals. It establishes the fact that they undo each other. So we're going to investigate kind of the idea behind that one, and then we don't actually use it in problems all that much. We use the second version, or the second part, I guess I should say, of this fundamental theorem. But this part is definitely kind of where the concept comes from. So in order to do this, we're going to investigate the area so far function. We'll call it capital A of x. And what that is going to be, okay, A of x, and I actually realized that I did not actually write that this function is the A of x function. Okay. So we have a graph of some function over here, okay, and we're calling it f of t just so we don't get the x's mixed up, okay? The A of x function, the area so far function, is going to be the definite integral from 0 to x of the f of t function. So that is going to be the signed area under the curve f from 0 to x. Okay. So let's do a couple of iterations where we actually plug in a number. So in this first problem, we're trying to find a of 1, which means we would plug the 1 in for the x and find the integral from 0 to 1 of f of t dt. So on my graph, that would be this region right here, right? And that would be what, a quarter of a circle. And that circle has a radius of 1, right? Just looking at the picture. So it's going to be a quarter of pi times 1 squared, or pi over 4. So the area so far, if you were to trace this function from 0 to 1, that's how much area you would have carved out. What about if a is 2? I have a second picture. So now I'm going to go 0 to 2. So now I'm looking at the entire semicircle, which would be pi over 2 times r squared. Same r, same circle. So now it's pi over 2. And if we add in a of 3, so now I have both this semicircle above and this triangle below. And so I'm going to think of that when I go to calculate the area as the area of the semicircle, which we already found in the last one was pi over 2, minus, because it's below the x-axis, the area of this triangle, which looks like it has a base of 1 and a height of 1. So minus 1/2 base times height. So it looks like I have pi minus 1 all over 2. So that is the idea of the area so far function, the a of x function, where what's actually the variable is the x value on the axis that would give you the area from 0 up until that point. Okay, so here we go with the actual looking at part 1 of the Fundamental Theorem of Calculus. And we're just going to kind of outline this proof so that you can see where this idea comes from. Okay. So we're going to use the area so far function, and we're going to use these pictures down here. Okay, so a of x calculates the area under the curve f of t. There's my f of t. Okay. And the area is going to be bound. In the last example, I started at 0. In this example, we're just going to start at some constant. We'll call it a. And then it ends at x, whatever x you put in. Okay. All right. So let's start by looking at this picture. In the first picture, we have a, and then we're going to x plus h. So similar to what we did in differentiation, you can see we have an x and an x plus h, x and x plus h. So obviously in the second picture, the a to the x, this would be a of x. And in this first picture, a to the x plus h, this would be a of x plus h, right? So if you subtract these, you're left with this region right here, which is what is drawn in the third picture. Okay? And if you think about width, the width of that would be h, because that's how far you've gone from x to x plus h. And the height, okay, is, they've used f of x, almost like a left-hand endpoint, f of x as the approximate height. So the area of this region is approximately equal to h times f of x, right? We could see that it's not going to be exact, but that's why we're using the approximately equal to. Okay. So this is where we're outlining these pieces. The area so far function of x plus h minus area so far function of just x, which would be this minus this, gives us this region, which is approximately equal to h times f of x. Okay. So now if we can agree on that, then what we're going to do next is we're just going to divide by h. Obviously, you have to do it on both sides because you're trying to say something is equal or nearly equal to. Okay. So that gives us the next line. And then if we have two things that are approximately equal to each other, then their limits as you approach the same number should also be approximately equal to each. So from here to here, we're going to take the limit as h approaches 0 of both sides. Now take a look at this left side. What does this limit look like? Limit as h approaches 0 of a of x plus h minus a of x over h. That looks like a prime of x, doesn't it? In fact, that is the derivative definition for the function a. And then if we look at the other side, as h approaches 0 of f of x does not have anything to do with h. It's not, there's no h in this expression. So it's like a constant in terms of what you're taking the limit with respect to. So the limit as h approaches 0 of f of x will just be f of x. And that's because f of x does not depend on h. So if you look at what we said, we have that the derivative up here is basically approximately equal to the f of x. Okay. So let me go back here. Therefore, a prime of x is approximately equal to f of x. And if we look at what those two things are, okay, a prime would be the derivative of the integral. So the derivative of the integral, and that's equal to just this function. So in other words, taking the derivative of the integral canceled out the integral. And that's the conclusion we're getting to. So I'm going to write that in here. The derivative of the integral is approximately equal to the integrand, just the function. The derivative and the integral canceled each other out. So I just kind of typed that up in a little bit more concrete thing here. The derivative of the integral basically leaves you with just the integrand itself. So the differentiation and the integration undo each other. So it's a crude, it's not a super mathematically precise proof, but it's just trying to get to the concept of the fact that these two things are inverse operations. So what the fundamental theorem of calculus part 1 says is if you have a continuous function on a closed interval and you have this area function that we have defined as such, okay, that area function is continuous and differentiable, and in fact its derivative is just the integrand itself. So you'll notice it looks like you're just taking this x and plugging it in to the integrand to get your answer, and that is exactly what you're doing. Okay. It does not matter what the lower bound of integration is. It could have been 0, it could have been, we had a, it could be 3, it could be, it doesn't matter. Okay, as long as you're taking the derivative, so it says use FTC1, FTC, we always use FTC to stand for Fundamental Theorem of Calculus, part 1, to differentiate the following function. So I'm going to take a derivative of this. As soon as I see the derivative of an integral where the x is up in the top, all I'm basically doing is plugging that x in to the integrand itself. Okay, and that's because I should write that equals g prime of x, so we're clear. It's because the derivative and the integral cancel each other out. Okay, so same thing here. I'm taking a, I guess I shouldn't write equals, h prime of x. Well, that didn't work out so well, did it? A little better. It's just going to be cosine of x squared plus x. So like I said, the problems themselves are not actually very interesting. I'm not going to give you an assessment on these types of problems. There might be a handful in the homework, but it's the concept of the derivative of the integral. They cancel each other out. That's the most important part of FTC part 1.